in the cell of our cell phone, and such as when the aircraft go back into the Earth. This number is deviated from zero. So in this case, we have to describe it using Boltzmann equation.
Welcome to the ISIUM TV classroom, where we're going to be talking about kinetic equation. It's an essential tool in depicting phenomena in physics, but in its various forms and over the years, it's revealed a number of limitations. Well, here to discuss his work in the field, I'm delighted to be joined by Professor Ruo Li. Ruo, thank you so much for joining us. What are the applications of kinetic equation and what makes it so challenging?
Yes, since the kinetic equation, there is a function with a lot of variables, so it's extremely difficult to carry out any numeric studies. So our method is trying to remove some of the variables to make it a much more simpler case. We know for 60 years that the gross moment method can never give correct physical prediction in the history. The major difficulty is the nature of the hyperbolicity. My major discovery in this direction is trying to resolve this problem completely.
How has the field grown since the 19th century Boltzmann equation?
Since we are trying to describe the fluids in some extreme region. You know, that's the most important thing in physics. If we want to study a lot of particles in a volume, so just like this in a volume, and we have a lot of particles in it. So the particles, they are moving and interact each other. So we assume that this thing to be a length L, and so there is a so-called mean free path. If this length is an L, so the most important parameter for this system is the ratio between this L and this L. So it's called the closed number, and this is this ratio. In our everyday circumstances, such as the atmosphere in this room, this number is very, very small. So we can directly use the microscopic hydrodynamics to resolve the atmosphere in this room. But in the cell of our cell phone, and such as when the aircraft go back into the Earth, this number is deviated from zero. So in this case, we have to describe it using Boltzmann equation.
Can you talk us a little bit further through your recent discovery?
For the Boltzmann equation, and we know that it's a very high dimensional case, and so gross moment method is trying to reduce a high dimensional equation to a low dimensional one. With our work, for this closed number, if it's going to zero, and we can have the classical Euler or Navier-Stokes equation to resolve it. For this is going to 1. This one is very big, since the particles will travel along the room. So the Boltzmann equation can describe the problem for this thing to about -2 to 1. So in this procedure, we can always describe it by Boltzmann equation, but we need to have some intermediate model between this Euler and Boltzmann to model the system around this region.
And that's the Grad's moment method?
That's Grad's moment method. And we can have this Grad's moment method here. In the last 60 years, Grad's moment method is always be collected in a textbook. There will be ending with such words: this system is so important, it has never given us correct physical predictions. So the problem is the lack of the hyperbolicity. Our work is to make the system to be hyperbolic.
Thank you so much for talking us through your important work, Ruo. Thank you for joining us.
Thank you.